So the periodic table in 1860, that's an important date because that was when this guy named Stanislav Cannizzaro first learned to calculate relative atomic masses of the elements. So in other words, he could figure out that carbon was 12 times heavier than hydrogen. And so that would make, hydrogen 1 and carbon 12. So very simple but very important designation because that allowed him to put all of the elements in order from smallest to largest. And then once they were in order, in 1869, Dmitri Mendeleev comes along and uses something called the periodic law to create the first periodic table. He was writing a chemistry textbook and had like a couple days before his deadline and wanted to come up with a good system for organizing the elements, and it basically decided that if you put the elements in order of size, starting with hydrogen, then periodically you would have these repeating properties. So maybe every 8 or so elements, you would have an element that was very light and reactive and metallic, or whatever the properties were, but they would repeat every so often. So another name for periodic law is periodicity. So when things repeat, when they're put in order, like if you were to take a calendar for the entire year and just write day number 1 at the top and just, all the way to day number 365, what you would find is that every 7 days you would have common properties, like, it would be the first day of school of the week, or, it would be the day that you have to keep some appointment that's on a regular basis. And so that's where we come up with weeks in our calendar. That's why we have vertical columns in our calendar, because when you put these things in order by, number, we find that periodically we have common properties, so that everything in the same column has things in common. And that's what Mendeleev realized about the elements, and that's where the periodic table came from. Now, his periodic table looks a little bit different. This one is actually in German. But basically it's a presentation of his periodic table. He was Russian, but this is an early one written in German. And you can see here that his periodic table had the families, the elements that had things in common were shown not vertically like ours are today, but horizontally. So, and he wasn't quite right about all of them. For example, he put lithium, sodium, potassium, rubidium, and cesium all in the same row, all in the same family, but the the atomic mass 204, TL, which is thallium, doesn't actually fit in that family. Today we put it a couple rows over in the middle of or to the right-hand side of the metals, but not anywhere near lithium, sodium, potassium, rubidium, and cesium. These guys, though, do make a family of elements with similar characteristics on our modern periodic table. So he was largely right. The other cool thing he did was he was able to actually predict the properties of elements that hadn't even been discovered yet. So, for example, if you look at number 68 and 70, those had not been discovered yet, but he knew that there was an element missing in terms of, the pattern that he was seeing. So, for example, if you look at carbon, silicon, and tin, those have common properties. And so he sort of predicted that there must be something with a mass around 70 that fits in there that just hasn't been discovered yet. And actually, he was 100% right. It turned out, later on, it was discovered that this element, germanium, did fit perfectly into that spot and has a mass of about 72. So he was a little bit off on his mass guess, but pretty close at the same time. So some important characteristics of Mendeleev's periodic table. As I just said, he was able to predict the undiscovered elements and their properties because of the families that they apparently should fit into. He ordered his by atomic masses because we didn't know about protons in 1869. That way they weren't discovered or the way to calculate the number of protons, which is also called the atomic number, was not discovered until 1911. And once again, his groups or families ran horizontally, not vertically, whereas the modern periodic table are vertical. And he had no noble gases. So if you think about that, the reason that wouldn't have had any noble gases in 1869 is because they hadn't been discovered yet. And the reason they hadn't been discovered yet is because they don't behave like a lot of other gases like oxygen and nitrogen and chlorine. They don't react with other elements very much at all. So detecting them or discovering them would have taken a long time, and of course it did. And then that brings us to the modern periodic table. The modern periodic table, the columns make up our groups or families, so they run vertically up and down. They are numbered 1 through 18. There is a different numbering system that involves Roman numerals, but we don't use that system. A couple different ways the periodic table can be kind of sliced up. One is to refer to the S and P blocks. So group 1 and 2 would be the S block, and group 13 and 18 would be 13 through 18, would be the P block. Those are sometimes called the main group elements. And then the transition metals fall in between. So that's basically the D block. And then we have the intertransition metals, also called the lanthanides and actinides. Those are down at the bottom of the periodic table. That's our F block. And then the other significant thing to note about the modern periodic table is the elements, the rows are called periods. So the horizontal row, 1, 2, 3, all the way down to 7, those are called periods. Okay, so then that brings us to a couple different designations within the periodic table. The first thing you need to understand, and you can kind of sketch your own periodic table. It doesn't have to be perfectly accurate as long as you get the general shape. So the general shape, and then where are the metals, nonmetals, and metalloids, which we're about to talk about. And the important thing is, as you sort of sketch this, and again, you can just make it, you don't have to, of course, fill in everything. But if you just sort of, draw the shape sort of roughly, kind of an outline, and we're moving helium back to where it sort of belongs. We moved it for our electron configurations next to hydrogen, but we're going to move it back. And then here's, of course, our lanthanides and actinides down here. But the important thing as you're taking notes here is that you understand where the metals are. And if you want to color them in, kind of like they are in this picture, that would be a good idea. And the easiest way to separate them or to notice which ones are the metals would be everything to the left of your metalloids, which are this little staircase right here. Everything to the left of that little staircase would be a metal except for hydrogen, which of course is a nonmetal. And that does include the lanthanides and actinides down at the bottom. So metals are malleable, which means that they are bendable. You can flatten them, change their shape basically without them cracking, at least too easily. And some are more malleable than others, of course. Ductile just means kind of the same thing, only specifically it's talking about being stretched into wire or formed into long wires like copper wires in your house used to conduct electricity. And again, conductive. So most metals are going to be pretty conductive, although that does vary a little bit from one metal to the next, both of heat and electricity. All right, then the metalloids, again, are the little staircase there. And they're interesting because even though there's not a lot of them, number one, they separate the metals from the nonmetals, and number two, they have these intermediate properties. So for example, silicon, okay, is the metalloid that's used in computer chips. So it's used because it is actually a semiconductor, and so that is helpful in making computer chips. They sort of have these intermediate properties. So metals tend to be conductive, nonmetals tend to be non-conductive, metalloids are sort of in between. Sometimes, like in the case of silicon, it's shiny like a metal, but it is brittle like a nonmetal. In other words, if you hit it with a hammer, it's going to crack into pieces instead of bending like a metal would. Then the nonmetals are, in this chart, they're in blue. So you can shade them in however you want to in your little sketch of the periodic table. But they're in blue, and So they actually contain all three physical states. So there are solids, liquids, and gases that are nonmetals. Metals are all solids with the exception of mercury. So the rest of the metals are solids. Nonmetals can be solids, liquids, or gases. They tend to be, if they are solids, they tend to be non-conductive, dull, brittle. In other words, brittle, of course, means they're not malleable. If you hit them with a hammer, they're going to crack. They're not going to bend. Okay, and then we're going to go through just a couple of important groups from the periodic table, just 4 of them. Group 1 are the alkali metals, and I'm going to show you a demonstration of alkali metals in class. They're very reactive. They're very soft, which is kind of unexpected for metals. They're not found in nature because they're so reactive. Hydrogen can be considered, it is in group 1 technically, but it's not usually considered to be an alkali metal because, at least as far as we know, because we don't really have solid hydrogen here on Earth, but if we did, we're not really sure whether it would be metallic or non-metallic, but sometimes it's considered an alkali metal. The rest of them, though, of course, are true metals that we know for sure, but they're very soft for metals, and we'll take a look at a couple of those in class and talk about that next time. The alkaline earth metals are in group 2, and they're just kind of like a lighter version of the alkali metals. They're still reactive, but not nearly as reactive as your alkali metals. And it has to do with their electron configurations. So, of course, everything in the same group, if you think about electron configurations, would end in a similar way. So everything in group 2, the alkaline earth metals, would end with something S2, like beryllium would end in 2s2, magnesium would end in 3s2, right? They're less reactive, but they're still very reactive. And then we're going to jump all the way across the periodic table to group 17 and talk about the halogens. So halogens are, and ignore, by the way, hydrogen there at the top. That's this particular periodic table was drawn moving it over, but it's not really there for the purpose of, it's not a halogen. Halogens are fluorine, chlorine, bromine, iodine, and astatine. They're very reactive. They're called halogens because the name means salt producing, because they're found in salts like sodium chloride, which is table salt. But there are other salts like, potassium bromide, lithium fluoride, whatever other combinations you want to talk about. They're very reactive, and so you don't find them as single atoms in nature. So you don't find single, for example, chlorine atoms floating around in nature, but you will, you can have Cl2. So this is called diatomic, meaning that there are 2 atoms together whenever you have the pure element. So a pure molecule of chlorine would be Cl2. There are other elements that are like that. For example, you've heard of oxygen as O2, nitrogen as N2, but the halogens are all that way because they're so reactive. And then finally, we're jumping over one group to the noble gases. These are, of course, the least reactive, and we've talked about that a little bit. But these guys are colorless gases, very hard to identify or pick out because they don't react with anything, or at least not with very much. They do exist as single atoms because they are so unreactive. And so the only real uses for them usually have to do with their inability to react. So, for example, when we used incandescent light bulbs, which aren't used very much today, an incandescent light bulb basically involves a superheated piece of metal, tungsten metal, inside the light bulb, and so it gives off the light, but the gas that fills the light bulb has to be a noble gas, because otherwise at those super high temperatures, if you had any oxygen or nitrogen or any other gas that's not a noble gas in there with the tungsten, it would very quickly react and it would rust the tungsten, and the light bulb would essentially, go out the very first time you used it within a couple seconds. But if you put some krypton or argon in there, then they're not going to react with the tungsten, and the light bulb lasts for, at least several months. So those are important groups of the periodic table. And we'll take a look at a few demonstrations in class of some of these elements.